Professor Rad, and this is Precalc video 1-6, composing functions. In this video, we're going to be looking at basically three components of composing functions. First, we're going to talk about what it is to compose functions. Secondly, we're going to talk about how do you find the domain of a composite function. And then thirdly, how do you break down a composite function into its sort of like basic original pieces. So what does it mean to compose functions? Well, ordinarily, when we think about combining objects in algebra classes, we have four primary operations. We have adding, subtracting, multiplying, and dividing, right? So lots of techniques for doing that, but they're pretty basic, very similar to adding, subtracting, multiplying, or dividing expressions. When it comes to functions, there's something new though. A function is basically some mechanism, I guess some machine, for taking an input and spitting out some kind of output. So this creates a new way of combining functions that we can't just combine like numbers in, and that's performing these functions in order. So that if I give you an input, you can throw that into one function and get some sort of output, and you can take that result and put that into the next function and get a new output. So when you do this, that's called composing functions. So you throw an input into one function, you work it through it, and then you throw it into a second function, the result into a second function, and then you get a new thing out of it. So that's what we're going to be doing. We'll do a few examples of composing functions. However, there can be some trickinesses to identifying the domain of a composed function. So I want to take a step back. Well, I can't, I'm against the wall, but we'll just kind of do a quick review of finding the domain. So when you find the domain of a function algebraically, your basic assumption is the domain is going to be all real numbers unless, and then there are a series of checks that you need to do. And the checks are kind of like things where all real numbers would break down. So you want to exclude those things from your domain. This is a list that we will be adding to throughout the semester. So if you want to write this like on the back of a notebook or on a single sheet, so you can add to it as sort of a one-stop reference for your domain checks, that would be a good plan. So right now we have two things to check for. The first is that denominators are going to break if they're zero. So anything that has a denominator in it, you have to ensure that the denominator is non-zero. So if I had a function f of x is 1 over x minus 3, because it has this denominator, I would make sure x minus 3 is not 0. So that means that x can't be 3. So therefore, our allowed inputs, our domain, is going to be everything that's not 3. The other place where our functions can break down is if we have an even radical. So you cannot take the square root of a negative number and get a real number back. You get an imaginary number or a complex number, but not a real number back. So if you take the fourth root of a negative, same deal. So if you have an even radical, you want to make sure whatever's underneath there is greater than or equal to 0. So for instance, if I have f of x is the fourth root of x minus 1, inside that even radical is x minus 1. So I have to make sure that it is greater than or equal to 0, which would mean x is greater than or equal to 1. So to find the domain, you could use set builder notation, but I opted for interval here because I was running short on space. So that's everything from 1 and above. Now I have one other example here just to show you if you don't have an even radical. So this one is the cubed root of x plus 1. If you don't have an even radical, then your domain's all real numbers. This is because you can take an odd root of a negative number, right? You could take the cubed root of -8, and that'll give you -2. So when you're checking for your domain, make sure denominators are non-zero, and you want to make sure that anything underneath an even radical is greater than or equal to 0. So let's take a moment and see how these combine to form the domain of a composite function. Okay, so if we are taking two functions and we're composing them, we're performing them in sequence, in order to find the domain of that final function, of that composite function, you want to see where the overlap is between the domain of the inside function, that's the first function you're doing. And that makes sense because in order to put the result of the first function into the second one, you had to be able to put it into the first function to begin with, right? So you have to make sure you check the domain of the inside function, and you want to check the domain of the final function. So you don't need to check the domain of the function you're plugging into, because the long and short of it is the range of the first function ends up being accommodated for in this last step. So there's a little bit of math in the background that I'm not going to worry too much about. So right now we just need to know, if I want to find the domain of a composite function, I'm going to compose my functions, get the composite, and then I will need to check the domain of that final function and the domain of the original inside function and see where they overlap. So let's do a few examples of composing a couple of functions and then finding the domain of that end result. Alrighty, so here's our example that we're going to work through. It has two parts, A and B. If you want to take a moment and copy it down, you can pause the video here and do that. So I also wrote a little summary here of what we need to do to find the domain of a composed function. So we're going to need to find the inside functions domain and the final functions domain, and then see where they overlap. So for this example, f of x is equal to 2 times x to the negative 1, and g of x is going to be 1 over x plus 3. So our first step is to find f composed with g. So this open circle here, that's our notation for composing functions, and its domain. What this means is that if I give you an input value of x, you're going to throw that into our function g first, and then you're going to take that result and throw that into f. So here's what that looks like notationally. So f composed with g of x literally means you're going to take g of x, and now this becomes the new input of f. So the first thing we have to do is take g of x. So I'm going to take g of x and replace that with its function definition, which is 1 over x plus 3. And that's what I'm substituting into my function f. So I take g of x and I replace it with 1 over x plus 3. Now I'm going to go to my function f of x, and wherever I see an x in the function, I'm going to replace it with this 1 over x plus 3. So the 2 stays the same, but now the x is going to become 1 over x plus 3. And then I have this minus 1. So we'll do that minus 1. Okay, and now I want to simplify that expression. So the negative 1 means take the reciprocal of what's inside the parentheses. We don't have to do anything with the 2 yet because there's a secret times here. And our order of operations says deal with exponents before you deal with multiplication. So the reciprocal of 1 over x plus 3 is just x plus 3. I mean, you can think of it as x plus 3 over 1. Anything over 1 is itself. And then now we can distribute that too. So we get 2x plus 6. So that's the first part of this problem, finding f of g. Next, we want to figure out its domain. And we're going to see in this example why the domain can be a little bit misleading if all you do is look at your final results. So to find the domain of a composed function, we have to make sure that we can initially plug into that inside function. So in this case, g of x is on the inside. So we need to find the domain of 1 over x plus 3. So I'm going to write the domain of g, because this is the one I'm looking at to begin with. When I do my check, it has a denominator. So I need to make sure that x plus 3 is not 0. And then my second check is for an even radical. There are no even radicals in this function, so I don't have to worry about that second check. So if x plus 3 is not 0, we can subtract 3 from both sides so that x does not equal negative 3. So this is the domain of our inside function. If I'm going to evaluate g of x, I can do that for any number except for -3, because if I try to plug -3 into there, then I'm going to end up with division by 0 and the world explodes. I don't know. Next, we have to find the domain of our final function. So when I look at 2x plus 6, I'll write this here, the domain of 2x plus 6. Well, 2x plus 6 is a linear function. Remember when we looked at the identity function and it just kind of went off forever on both sides? So the same thing's going to be true for 2x plus 6. It's a little bit steeper than the identity function, but it has the same domain. It's going to be all real numbers. So the domain of 2x plus 6 is going to be all real numbers. So what this means is to find the domain of f composed with g, we now have to see where these two things overlap. So all real numbers and all real numbers except for -3 are going to overlap everywhere except for at -3, right? So this domain allows -3, but this one does not. So the domain of f composed with g is going to be everything that is not -3. So this is one of the reasons that finding the domain of a composed function can be a little bit tricky, because you have to know where you came from originally. If I'm composing functions, if originally I'm not allowed to be -3, then in my end result, I'm not allowed to be -3 either. If we were to see what this looks like graphically, then basically we would have this line and it would have a little hole when x is -3. So let's see, we could sketch this real quick. So 2x plus 6, I'm going to call this one 3. Don't want to do that now. Let me count by 2's. 4, 6, 2, 3. And let's see, if I were to plug -3 into this, 2 times -3 is a -6 plus 6 is 0. So we're going to have a line that looks like that with a little hole here at -3. Essentially what we're saying is that this composition of functions is the same as this line, except when x is -3, because g of x had this little hiccup. So what I'm going to ask you to do is to pause the video and try part B. This time, instead of finding f composed with g, you're going to find g composed with f. So in other words, you're going to take this process, but you're switching which function's on the inside and which one's on the outside. So take a moment, pause the video and work through example B. And then when you think you've got it, you can unpause and we'll walk through the solution together. Alrighty, hopefully you paused the video to work through that second example. Now, if you got stuck, that's okay. If you found it correctly, that's okay. And if you found it, but you got a wrong answer, that's also okay. We're going to go through it and we'll see where mistakes may have been made or where we might have gotten stuck. So the first thing I did in order to find the composed function g composed with f is to rewrite it as g of f of x. So f is our first input, that's our inside function, so it goes inside the parentheses. Then I took my function f of x, 2x inverse, and I wrote that down here. And now I made a choice. You may not have made this choice at this point, but the choice I made was to rewrite this expression with only positive exponents. So in other words, I decided to take this x to the -1 and throw it into the denominator. Now you want to be careful here because 2x to the -1 means 1 over 2, means 2 over x, whereas 2x to the -1 is going to mean 1 over 2x. So you want to be careful where that 2 ends up being. In this expression, which is the one we have, this exponent is only applied to the variable because remember, there's a secret multiplication here. And according to our order of operations, exponents happen first and then multiplication. So we take the reciprocal of the x first In other words, throw it in the denominator, and the 2 stays put in the numerator. So that's just kind of a little refresher on negative exponents. You want to be careful with those. So I rewrote this as 2 over x. And then I went to g of x and I said, oh, great. I'm going to take this x and replace it with 2 over x. So I took my 1 over x plus 3. And instead of x here, I made that 2 over x. Now, this is what's called a complex fraction, not in simplest form. So we want to simplify that. Because we only have one denominator, the easiest way to do that is to multiply the big top and the big bottom by that little denominator. So I multiply top and bottom by x. 1 times x is x. When I distribute the x times 2 over x, those x's cancel out and I get 2. And then x times 3 is 3x. So that's how I went from this line here to this one here. So when I find the expression for g composed with f, I end up with x over 2 plus 3x. Whew, okay, so next, that was this first part, finding just the composition of the functions. Next, we need to find their domains. So f of x is my inside function. So I'm going to find the domain of f. This is another time when it's helpful to rewrite the expression with only positive exponents. Because if I see this, I might be tempted to think, oh, there's no denominator, nothing to worry about. However, that -1 is a denominator. So if you're likely to forget about that, you might want to add to your check here to look for negative exponents. And my marker decided to quit on this problem. Sorry about that. So a note you can add here is to look for negative exponents because that implies a denominator. So here our denominator of f, this inside guy, was just x. So that meant x can't be 0. Then for my final function, I also have a denominator. So that means that 2 plus 3x cannot be 0. So 2 plus 3x can't be 0. And when I solved that, that meant x could not be negative 2/3. So this time we have two domains that have different problem spots. So this one we can't be 0, and this one we can't be negative 2/3. So when we combine them, we just list all of them. So here x cannot be 2/3. Oops, that should be a negative 2/3. I'm making mistakes on the board here. So x cannot be a negative 2/3, and x cannot be 0. So those are just a couple of quick examples of doing the finding the composite function and checking for its domain. We have one last example, splits into two parts, but one last example where we're going to kind of essentially end up here and say, what are the beginning functions we could have started with? So I'm going to take a moment, erase the board, and write the new problem, which should be appearing now. It's appeared now. Okay, so here's our next example. We're going to find two functions, f and g, so that when I compose them, I end up getting h of x. And we have two different parts. So for part A, h of x is x plus 5 cubed minus 1. Now I'm going to show you the little trick that I do to figure this one out. So what I do is I say, okay, if I'm x and I'm being plugged into this function, what's the first thing that happens to me? So in this case, when I look at this function, the very first thing that I do to x is I add 5. That very first thing that you're doing to the function, that's going to become your inside function. Oh, I apologize for my neighbors. They're barking, rather, their dogs are barking. But so if I have f composed with g is the inside function. So that means this is going to be g of x. So that's my first step. My second step is to rewrite what h of x was. So I'm going to take that x plus 5 cubed minus 1. And in order to find f of x, what I'm going to do is I'm going to take that thing I called g. So in this case, x plus 5, I'm going to erase that and just replace it with an x. So this means that f of x is going to be, I don't need these parentheses anymore. So f of x is going to be x cubed minus 1. So let's check this to make sure that our sequence is going to work properly here. So here's my check. I want to make sure that f composed with g, does that equal x plus 5 cubed minus 1? So that was my h of x here. Well, this is going to be, g is on the inside, so this is going to be f of x plus 5. Okay, so x plus 5 was our g of x, that goes on the inside. Does that equal x plus 5 cubed minus 1? So now this means I take my function f, and anywhere I see an x, I replace it with x plus 5. So I'm going to replace this x with x plus 5, cube it, and subtract 1. And it worked out. Hooray. So once again, our trick here for this is whatever happens to x first, that becomes your inside function. So x plus 5, that became our inside function of g. And then I rewrite my original function, which was this one, and I get rid of the piece that I just called g, and I replace it with an x. And that becomes my second function. So let's see if that process is going to work for the second example as well. So the second example has an awful lot going on. So let's kind of just take it slowly here. We have the square root of x minus 2 over x minus 2. So if I'm a value for x and I'm being substituted into this function, whether I'm on the numerator or the denominator, whichever one I choose to do first, the first thing that happens to me is subtracting 2. So I'm going to say, let's let g of x equal x minus 2. Because whether I choose to evaluate the numerator first, I have to subtract 2. Or whether I evaluate the denominator first, I also have to subtract 2. So now that I'm here, let's rewrite h of x, square root of x minus 2 over x minus 2. And now to find the outside function, to find f of x, wherever I see this showing up in the original expression, I'm going to erase it and replace with x. So here in the numerator, we have an x minus 2. So I'm going to erase that and replace it with an x. And in the denominator, we also have that x minus 2. So I'm going to replace that one with x as well. And this is what we'll call our f of x. And again, if you wanted to check, if I take g of x and I substitute it into here, all these x's are going to be replaced by x minus 2's, and I will get back at the beginning. Now, you'll notice that in the directions, it says find f and g. It doesn't say that these are the only two such functions that will work. So for example, there's a different way we could have done this first problem. I could have said, let's let g of x be x plus 5 cubed. Then, if I were to rewrite my h of x function, I'd have my x plus 5 cubed minus 1. And then I can replace x plus 5 cubed here with just an x and get x minus 1. So then my new f of x would be x minus 1. And if you wanted to check, you'll find that this set of functions will also work. So there are often multiple correct answers for these. My preferred, like my own personal preference, is to make g just one step. This one has g being 2 steps, adding 5 and then cubing. For example, if I wanted here to go 2 steps, having g of x be x minus 2, then I'd have to square root. Then I'd have a little bit of a bigger trouble on this next part because I'd have to figure out what does that mean to this denominator, and it becomes a little bit fishier. So my recommendation is make g of x, or the inside function, as simple as possible, and then just get rid of it from f of x, or from the final function, and that'll give you your f of x. It's probably the easiest way to do it. So I think that's going to wrap it up for this video. I hope it was helpful in helping you compose functions and break functions down. This is actually a really important skill in calculus. You need to know how to look at a mess of a function and identify its component parts and identify what was composed to get there. So this skill is going to be real important in calc. And I hope we also helped review domain a little bit. So I hope you have a wonderful day, and I look forward to seeing you in the next video. Bye for now.